Hello, everybody. Good morning. It's great to be here. I'd like to thank the organizers for the opportunity to show some of my research here. Today, I'm going to be talking about the efficient integration of censored ordinal and nonlinear monotone data in parameter estimation for ODE models. This research came from two aspects, or the motivation for it was from two aspects, that there is an abundance of qualitative and some semi-quantitative data that is often neglected. Because of the second aspect of a severe lack of methods for integrating such data in ODE models. So here I am to present some methods that can integrate that and has an easy to use implementation in a package that we're developing in our group. So I'm going to start with the ODE model maximum likelihood parameter estimation workflow. We already saw this in this session a couple of times. So we have some kind of a model that has state variables, which can be concentrations, or in population dynamics, they can be compartments of population. And we have some unknown parameters. These are the data parameters. Okay. The data parameters that we would like to estimate and retrieve. We have some model data that is given by observables, and the observables are also noise corrupted. And we assume that this noise is, in this research, we're going to assume that this noise is normally distributed with some standard deviation. So in the standard workflow, we use numerical optimization to estimate the parameters of the model. So we start with some starting point, starting guess. We simulate the model, we get the model simulation, and then we can directly calculate the negative log likelihood objective function, which we check for stopping criteria, and then either update our dynamical parameters for the next iteration, or we end the optimization. What does this result in? So we get better and better estimates of the ODE model, and with these, we get better and better fits of the data. So I'm going to pose two questions. First, how could one investigate whether their data is nonlinear? And secondly, in case that it is nonlinear, how could one still use such data? So what do I mean by nonlinear data? This is an example from Western blots. So Western blots usually have a linear relationship between the protein amount that we want to observe and the optical density that we are actually observing. But sometimes it can happen that that Western blots also saturate with the amount of the protein amount. So we cannot really assume that there is a linear relationship between these two values. Another example is common in radiometric threat, but I'm not going to go into details because it's a little bit more complicated. So basically, we have the concept of having a quantity of interest that we would like to see and a measurement that we actually can measure, but there is some kind of nonlinear relationship between the two that we might not know. So this can be, for instance, a saturating curve. It can be some kind of sigmoidal curve. It can be even censored, and we are not sure whether it's censored or not. So how do we check that? And so the definition is that there is some kind of an unknown nonlinear relationship between the measured quantity and the quantity that we're interested in. So a mathematical definition would be that there exists some kind of a nonlinear monotone function f, such that we have the data zk, and the data zk is equal to the output yk, and the application of this nonlinear monotone function on yk with some noise on the data. So the question is, how could one use this nonlinear monotone data? The first approach could be, because often these nonlinear relationships are monotone, we can extract the ordering of the data. And for instance, in this example, small dummy example, we have the measurement T1 at time point T1, and it is the second largest value in the measurements that we have. So it has the ordering number 2. Or the measurement at time point T4 has the lowest value, so it's on the first level of the ordering. When we have this ordinal data, one could use the optimal scaling approach. This approach was initially developed in statistics for categorical data, and later it was applied to dynamical systems by a former PhD from our group, Leonard Schmisser.
And this approach can also be easily applied to sensor data. There are other approaches for sensor data, but this is something that we have also implemented in our package. So the illustration of the optimal scaling approach, compared to the standard one, we have one additional step in the optimization process. So at each optimization of the outer loop, we have an inner optimization problem in which we compute the surrogate data. So the problem with ordinal data is that we don't really have numerical values that we can use to construct an objective function that's numerical that we can then optimize for better parameter estimates. So to remedy this, we want to introduce some surrogate data that's going to represent the ordinal data. We're going to introduce the surrogate data such that it still satisfies the ordering that's given in the ordinal data. We define this ordering by the categories. So these two first measurements are a part of the middle category, so they have to stay in the middle category. These three measurements have to stay in the upper category, and so on. Now we can move around the categories, can optimize the categories, but we move them around such that the surrogate data that stays in the categories is closest to the simulation. So for instance, this point here, the third point in the second category, would like to be a little bit lower and closer to the simulation, but it can't because of the first category pushing it up. When we have the surrogate data, we can use it to get objective function values. Here. We can use it to get least squares between the surrogate data and the simulation to get an objective function value that we can then optimize for the optimization and parameter estimates. Now the question is there a better method for this type of data, for the nonlinear monotone data? The downsides of the optimal scaling approach for the nonlinear monotone data is that we lose the numerical information. So we lose any information about the scale of our measurements. Additionally, we are not anymore in a probabilistic setting because we have some kind of least squares objective function that we do not know really the scale of. So we have no lower limits that we can use for confidence intervals and uncertainty analysis and so on. So the alternative to this that we propose is the spline approximation method. The basic idea is that we want to approximate this true nonlinearity that we don't know with a piecewise linear function as spline. The benefit of this method is that we can still conduct uncertainty analysis because we are still in the negative log likelihood framework. And it can be additionally used for the identification of possible data nonlinearities. So this is the illustration of the spline approximation approach. It's very similar. We have still an inner optimization problem in which instead of surrogate data, now we optimize spline approximation of the true data nonlinearity. And we optimize the spline, this green spline, in such a way that when we have current simulations of the model, that the simulations are mapped close to the measurements. You can probably already see that there is a huge overfitting capability of this because we're just taking the simulation, just plotting them onto the measurements. So we have to somehow regularize this. And this was a crucial aspect of it, is that we use a linear regularization of the spline. The idea behind this is that we push the spline to be linear, such that if the end spline is nonlinear, that the nonlinearity really comes from the nonlinearity in the data and not some optimization artifact and something. So to show some results on how well the method works, I'm going to use a model, phosphorylation dependent STAT5 dimerization model by Bloom et al. In our group, we would say that this is like a middle-sized model. It has 3 observables, it has 48 quantitative measurements, and it has 6 unknown parameters that we would like to estimate. A good property of this model is that it's well fitted, so we can find parameter estimates that provide trajectories that are a pretty good fit of the real data that they have. From now on, I'm going to refer to this as the best possible fit. So this is the fit if we have all of the quantitative information from the model, so the blue line. So the question is, if we have some nonlinearities, how well in nonlinearities in the data, how well are these nonlinearities estimated by this spline?
we're going to conduct a synthetic study to test this with 5 realizations of noisy synthetic nonlinear monotone data. So we took the data from the BOOM model. So these are the same data that you saw in blue from the last plot. And we applied some nonlinearities. So first, saturating nonlinearity, second, the sigmoidal nonlinearity, and third, we basically censored some of the measurements, censored nonlinearity. And then we got nonlinear monotone data in green here. We then added additive normal noise to all of the measurements, and we did this 5 times with 5 realizations to get 5 realizations of the data. And with these 5 data realizations, we ran optimization to get 5 optimal splines for those data realizations. And we're actually pretty satisfied with the results. So the true nonlinearity shapes are definitely identified. So the saturating is pretty good. The sigmoidal shape is identified. And third, we see that they all actually find that there is some censoring in the data. So the method wasn't given the information that this data is actually censored. They were just given that some numerical values, and the method inferred that the censoring is there. So I started with these 2 questions, and I would like to answer them with a plot. So how could one investigate whether the data is nonlinear? Let's say that you have some data that might have some possible nonlinearities. You could assume that the data is nonlinear monotone and apply this spline approximation method to it. And then looking at the outcome of the spline approximation method, if the outcome is identity, so x equal to x, f is equal to x, then this is really the true data, and the data can just be used standardly as quantitative and so on. If we have some kind of linear function with a scaling and an offset, then the data, we see that the data is probably relative. So we can use the hierarchical approach of estimating a scaling and offset parameter for this type of data. If we see some kind of a censoring in the spline, then we can use some methods for using the censored data. There are a number of those, imputation methods, non-imputation methods, and so on. If the spline is truly nonlinear, then we have nonlinear monotone data, probably. And we have 2 options. If we're very certain in the shape of the nonlinearity, probably the best way of using this data would be to parameterize it in the observable functions. So to add some additional parameters of some parameterized functions that would, for instance, in this case, you could use some kind of Michaelis-Menten type of function for the saturation. The other way of using this data would be to actually use this spline approximation method for the parameter estimation process. That would be used in case that you're not really certain of the shape of the nonlinearity, and you would like to be certain that you're going to have enough flexibility of what the nonlinearity truly is. So now the question is, if we did use this spline approximation method and other methods, so the one that I described, the optimal scaling one for ordinal data and the optimal scaling one for the sensor data, how much does this non-quantitative data contribute to the model fitting and for the parameter estimation of the model? So to show this, or one example of it, we're going to use, again, the same real-world data from Boom et al., but we're going to treat the first observable as nonlinear monotone. So we're going to assume that there is some kind of nonlinearity between the data. The second observable we're going to treat as ordinal. So we're going to give only the ordinal information to the parameter estimation process. And the third observable we're going to censor in the sense that we're going to right censor some of the measurements. We will compare then 2 models. One model fitted only using the quantitative measurements that are available, so neglecting every other data type that we have. And then the second model that's fitted integrating all this data with all of these methods that I've described. So here we see the best possible fit that we saw from before. That's the fit that is the gold standard that we would like to be close to. So that's the fit that we fitted using all of the data as quantitative as it is. In red, here you see the fit using only the quantitative data that is available after removing information from some of the observables. And we see that the fit is pretty okay. Actually, in the observable, it has the quantitative data, but in other non-scene observables, the fit is pretty bad. Now, if we use these methods for the integration of data, the spline approximation method for the nonlinear monotone treated data, the optimal scaling method for the ordinal, and the censored, these couple of censored data points here, then we get this fit using all data, which is much closer to the golden standard, to the blue line. And additionally, a cool thing is that we even infer the true parameters of the ODE model. So we get true parameter estimates using this method, with having much less information about the data, from the data. So this is proof of concept that integration of nonlinear monotone data, ordinal data, and censored data can greatly improve model fitting and the parameter estimation process. I'm going to just shortly mention the implementation in PyPesto. So we have our parameter estimation toolbox PyPesto. It has example notebooks on the usage of censored, ordinal, and nonlinear monotone data. And as for PyPesto, there are other model specifications, but for this approach, we use the model specification in PTAB. The additional effort that one needs to go through to specify that some measurements are nonlinear or ordinal and so on is actually very little. So in the PTAB format, one just needs to include some additional columns in their measurement table of the PTAB format. And then to actually use parameter estimation from PyPesto, it would be the same for the standard one, it would be the same, but the only additional thing that one needs to specify is that we enable hierarchical optimization. That's this optimization with another inner problem. And then the package is going to search for nonlinear data, ordinal data, or anything else that is in the PTAB specification table, and then construct these inner problems, construct the objective functions, and optimize using these other methods. So it's pretty easy to use. And I'm going to finish with an acknowledgement slide. So I'm going to thank my advisors, Jan and Stefan, and especially Dylan also for some very good and nice discussions on these methods. And of course, my whole group. And these are my socials if you want to contact me, or I'm going to be here for any discussions you might have. Thank you.
Hi. So this is a rather interesting method, but so the problem is also always the availability of data, right? And to approximate your spline, you need to add a few extra parameters. Did you look? So you need to put dense data in the frame, right, to do this, to properly estimate the spline. So did you look at how your regularization, which I guess has your linearization of the spline, which I guess is just a meta parameter, how many parameters that allows you to gain kind of 3 parameters on the spline, and how many parameters does regularization usually add? So how many data points, extra data points basically do you need?
So the regularization actually doesn't add any parameters. So the only parameters that are additionally added to the model in the spline approximation are the spline nodes. So where the spline actually is. The regularization is calculated analytically as the linear regression of the spline nodes. So the spline nodes are pushed to the linear function, and the linear function is optimized such that it is the closest one, so the linear regression of the spline nodes. So it's just an additional step of some analytical computation, but it does not include any additional parameters. But yeah.
So your spline always has the same number of...
Yeah, so the spline is the dependent. It can be also specified how many parameters, spline nodes you want. You can also manage that. But as you said, it is fair that there are some additional parameters in this method, so the spline nodes. But because there are some additional parameters, we use this hierarchical optimization approach that then makes it more efficient, because this spline problem, to solve the spline problem is much easier than to try to optimize the kinetic parameters. So the inner problem is much easier to solve and fast, so it can be just done very fast in each iteration of the long kinetic parameter optimization.